homework that I suggested last week before we ended. Then we'll look at the polarized and unpolarized deep inelastic scattering. We'll talk about the method, the tools, what are the concerns for experiments when we design the experiment. We'll talk about the first results and talk about the status of the spin crisis, including inclusive and semi-inclusive deep inelastic scattering. We will discuss what we saw in those early experiments and what they meant. Then that led to the program called the Relativistic Heavy Ion Collider, RHIC spin program. So we'll discuss the limitations of the fixed target program. We'll discuss the RHIC spin program. And towards the end, before we finish the lecture, I'll introduce you to nuclei and talk about what are the unknowns, what are the interesting things about nuclei that were also puzzling in the early 1990s, which need to be fixed, need to be understood in the future. So let's go to the homework first. I had asked you to consider calculation on xq squared plane, the collisions of 10 GeV electrons on 250 GeV protons. So that is what is shown here. The only thing I have changed in this plot for historical reason is I plotted the log q squared or q squared on the x-axis, just inverted that figure that you have seen so far. So x is on the y-axis here and q squared is on the x-axis. But other than that, all the physics that we discussed so far is the same. So let's look at the left-hand side plot, which says it's the scattered electron. Now, at the center, just above the figures, is a cartoon of a green proton going leftward, and the jets, and the jet is quarks here, Q, and the electron, the angle, is measured with respect to the proton direction. Because in an asymmetric collision like that, the center of mass of the system is moving towards the proton. So the convention is we always take the proton's direction as the zero angle or the forward direction. And with respect to that, we measure all the angles, theta. So now let's look at the scattered angle of the electron, which is 177. Remember, in the initial state, the electron is coming against the direction of the proton. That means at 177, the electron was scattered only by 3 degrees. So it's a small angle scatter. And let's see where it sits on the q squared axis. On this kinematics, on the left side, you see 177. And that line that continues below there is the line of constant angle at various values of x. But these are all the q squared of about 0.01 or 0.02. So over the wide range in x, the electrons that get scattered at 177 are all coming at this angle here. 175 sits right next door here, 170 sits here, 160 sits here, 130. 90-degree scatter, which means that the electron gets scattered vertically compared to the direction. It's sitting all the way there at q squares of 100 GeV or larger. Now remember, the q squared is the total energy that is there at that time at the energy transfer. So the high q squared events are the places where heavy particles might be created, or even the interacting points will be created. So WZ production, etc., will sit all the way to the high q squared, which is from 10 to the power 2 to 10 to the power 3. So this right corner at the top is where you will see, if you wanted to study W plus W minus production in Epley scattering, you would be studying it here. All the rest of it is all smaller the q squareds, and that means all the photon interactions that we want to study, virtual photon interactions, can go all the way to 10 to the minus 5 in x. That is the momentum fraction, and they all sit here. And another question I asked, can the scattered electron have energy more than the initial energy? And the answer is clearly yes. And you can see that the scattered electron energies are plotted here as dashed lines, which is 9 GeV, 8 GeV, 6 GeV, 3 GeV. They are all here. Then the 10 GeV electron sits out straight like that at a fixed x over a wide q squared range. And then here is a energy of the electron, which is 20 GeV. And one might ask, where did the electron gain energy? Well, it's simple, because it hit a very high x quark. You are in the region very high x here. The quark, which is, let's say, coming at 1/3 or 1/4 of the energy of the proton, which is already 80 GeV, and that gives the energy back to the proton, the electron, and that's why you can get always in the collider, the final energy of the electron can be more than the initial energy of the electron. And they are all sitting in this region here. As you go to higher and higher values of x, you can have that. And that's what happens. That's why you can get electron scattered energy larger. On the right hand side is the plot of scattered quarks, which is the jets basically, because the quarks will scatter. This is in the frame, in the interaction interaction. What is happening is the gluon or the photon quark interaction there, and then the quark starts moving through the nuclear medium or through the proton, and then it fragments into something else and comes out. It might come out as a jet if it is high energy enough, energetic enough. And so the same plot has been made now, whereas to where do the quarks go? So you can now stare at this and see that a quark going at 170 degrees, 175 degrees, which means that the proton is basically, the quark has turned over to this side here, which is very unusual, and that's why it sits at extremely low x right here. And then you can look at it and stare and see that the energy of the scattered jets is typically always less than the total energy of the initial proton, because it's very hard to create energy more than 3 times the valence quark energy. So that's why you don't see quarks or jets which are higher than the center of mass energy. Okay, so that's typically what the way to understand it is. So stare at these things if you have not calculated them. It's very useful to know this. It will come back to us when we design the detector tomorrow. So this was for 10 on 250. If you change the energy from that to 5 on 50, the plots change, and this is just an example of that. The range, the ratio of asymmetry between the electron and the proton, which is 1:10 here, will determine, and this is 1:25, and that determines where the angles, where the scattered plots, electrons and protons go. Okay, so these are things that that experimentalists have to consider when we look at the detector design. And theorists also have to understand this very importantly, because on such plot, if you start telling me as an experimentalist that you want to measure something in the 10 to the minus 5 region, I'm already going to tell you that it's a very small region of q squared that I can measure things at. I don't have much range in it. If you want to measure 10 to the minus 5 in x and a q squared range of 200 GeV or 400 GeV, I can't measure that with this collider. I'll have to do something completely different. I have to go to a much higher collider region. So theorists have to also figure out why there are limitations, and these plots make that clear, not just for experimentalists but also for theorists. Okay, now let me show you something that makes a point. How many of you have seen levitating tops? Can you raise your hand? I can see you. Do you know what I'm going to show you? Okay, 1 out of maybe 25, 30. Okay, very good. So what I want to emphasize here is that gravity, rotational motion, classical motion of these kind of things, magnetism, we all know that. And we think we understand it. At the same time, when you combine those effects, it gives you a very interesting and novel observation. In nature, you see things, you observe things and try to understand it. So we are going to do this thought experiment, but with a real film that I made on my desk here. Oops, sorry. So there is gravity in my office. You believe that, right? In New York, there is gravity. There is rotational motion that I've induced on this plastic top. The yellow part is plastic, and it has a metal rim around it. And there is a magnet, the orientation of which you need to figure out as a homework to tell me what makes this effect. So what I want to emphasize is that rotational motion, which is important for this observation, always makes interesting physics. Spin is an interesting and fundamental property also in nature, and it's full of surprises. As you saw, if you don't know the fundamental physics concept of what we just saw, you would be puzzled as to why the top levitates like the way it does and stops levitating when the rotational motion goes down. So that's the only idea I wanted to introduce to you, that spin makes an interesting life. In fact, you are not the first ones to be intrigued by this. This is a picture of Bohr and Pauli trying to understand the motion, the dynamics of the tippy-top toy, which quickly jumps over and rotates and turns 180 degrees while in motion to conserve orbital angular momentum. In the 19th century or the 20th century, I would say there were about 6 very, very important experiments that fundamentally changed the way we think about physics. And they all had one thing in common. They had something to do with chirality and spin. So the first one is Stern-Gerlach. The second one was Goldschmidt and Smith. Stern's experiment of proton anomalous magnetic movement. Kush's experiment that then an electron's magnetic moment is small, which means that the electron is point-like versus proton is not a point particle. We knew that already in 1933, that proton had a physical size, because we knew that the magnetic moment was 2.79 large. And then there was the electroweak interference experiment that discovered the weak interactions. And the last but not the least, which is the nucleon spin crisis, which I will now go into in great detail. So what I want to say is spin is a really important observation or observable that experimenters have used. In fact, it has been so prolifically used to kill theories is that Professor Elliot Leader from University College London has written in his book that experiments with spin have killed more theories in physics than any other single physical variable. And Bjorkane even jokingly said that if theorists had their way, they would ban all experiments involving spin. That's what was going on in the 60s and 70s. We were discovering new particles. We were discovering new things that were going on in particle physics, and theorists were making theories of that. And then suddenly we discovered that we could polarize them, we could control their spins, and perform experiments with spin. And as soon as we did that, we went back to the theory, and often the theory was wrong. And that is the reason for these 2 quotes, which I thought were remarkable. So let's now go into some details of electron-proton scattering and understand what we can learn from unpolarized first and then polarized deep inelastic scattering. So the nucleon-nucleus cross-section, or the lepton-nucleon cross-section, assuming a single gamma star exchange, is written here. The left-hand side is the lepton part tensor, the L mu nu, and the W mu nu is the hadronic tensor. And I have now acknowledged that these particles carry spin, which means that we need to include them in the tensor form. And that's what the SS are for. The small s for lepton spin, and the nucleon spin is capital S. The PQ and the KQ are its internal momenta, etc., etc. The WPS, the W mu nu, is then characterized by two structure functions, F1 and F2, as shown with red underlines. If you include the spin, then it adds to the same W mu nu to have two more structure functions, the G1 and G2 spin structure functions. G1 is characterized by when the quarks and the probing photon or the proton are parallel and anti-parallel to each other. The spin contribution of the quarks to the proton. That's just alignment. And G2 is when the alignment is transverse. So the photon that looks into the proton is still longitudinal, but G1, the quarks are somehow transversely polarized inside that. So that's basically the two. Let's look at what we learned from F1 and F2. It's a very high-level summary, but I think it's important that we know what we will gain out of that. So, inclusive cross-section, that means we ignore everything else of a nucleus or proton, is given at the top line there, and it has two of those structure functions, F2 and FL. The F2 embodies the quark structure distributions inside the proton. FL carries the information about the glue directly from the dynamics of the quarks. There's something called reduced cross-section. You can rearrange it and write it as sigma r to be F2a minus y squared by y plus, capital Y plus, minus times the FL. When you see it this way, you see that if you plot the reduced cross-section on the y-axis and y squared by y plus, which is just a kinematic factor, on the x-axis, and we vary it in a collider, the slope of, then you get the, when the y squared, the x-axis is 0, that is y squared by y is 0, you get an intercept on the y-axis. That sigma red is simply the F2 of that proton or the nucleus. I've written it generally as F2a, but it could be nucleus or the proton. And then the slope of that function, the rate of change of F2 structure function with respect to the y squared by y is then the FL, simply put that way, and that tells you what the gluon distribution is. And we'll come back to it more in a perturbative way later, but this is something that we can measure directly in an experiment. You want to change the y and measure the reduced cross-section at different points as shown and plot the function through the straight line and get the slope of that, and that will give you the gluon's information. In any typical collider experiment or observable experiment, we have the quark and gluon distributions called the parton distribution functions, and which are interpreted in leading order as probability of finding x and q squared in the proton. But then we have to connect them to observables. And so for jets and Delian, etc. kind of observations, the sigma 0, the observable, is the parton distribution function times the theoretical calculation of the cross-section that comes, fortunately for perturbative QCD, etc., etc. And you can do modifications of that as you go to more precise theory. The parton distribution functions you cannot yet calculate. Although tomorrow I will mention some lattice QCD efforts which are starting to calculate them ab initio. But yet, for now, we need to derive them from experiments. And how we do that, I will come back to that a little later. So for example, if you have an observable, a hadron production, then you have the parton distribution functions of I to A times the cross-section, the theoretical cross-section that goes from A to B, And then there is a fragmentation function that goes from the B to an observable that we see, where A and B are partons inside. So that's where you need the fragmentation functions. Again, those are not calculable but measurable. There are efforts to calculate it, but they are measurable. And then you have to find data over a wide range in X and Q squared to find the best values of F2 structure function, jets, Drell-Yan, try to incorporate all the theory we know for those, and do perturbative periodic calculations at leading order, next to leading order, NNLO, and evolution of equations that you probably have heard of, the D-Glab evolution that makes the evolution in Q squared plane, and the BFKL equation that tells you how the X distributions happen. So all that can be then embodied together and fit the best way we can in a multi-dimensional way with thousands of data sets these days and get the best fits for the parton distribution functions and fragmentation functions. So that's generally called the global fit analyses. And the more and more detailed data we get from F2, jets, Drell-Yan, the better theoretical calculations can be pushed to from leading order to next to leading order to next to leading order. So here is a typical example. I've shown you this plot of F2 over Q squared for a long wide range in X and Q squared. And the fits are shown to the best of the ability at NLO on those data sets. They do very well. The uncertainties are shown in yellow, which are very, very small. Now, how do you get to parton distribution functions? I told you that we have to fit them at next to leading order. And one thing that we know is that F2 structure function slope with DLN squared is the gluon distribution itself. So the gluon PDF that you get and everyone uses comes from HERA because of such a process. The most precise value of gluon distribution comes from the HERA's slopes. And those were then used at RIC and LHC to improve upon by looking at other variables. To do that, we have to use the linear D-Glab evolution equation. And as a product, you get all the parton distribution functions, which are shown in this best fit plot. You've seen this plot in my introductory lecture. I've told you that the gluon dominates at 0.1 or below, and that is shown by dividing it by a factor of 20, because otherwise this plot will look very strange. And I will show you that strange plot tomorrow in the lecture on EISC. Okay, so that's about what we want to do. That infinite rise of the gluon distribution is something that we really want to understand. So now let's focus not on the unpolarized, but on the G1 and G2 structure function. So G2 I will ignore for good reason. It's a very small thing. I want to focus on G1 for now. But the physics that I will describe is very similar. So once you put spin into this, what you have is a slightly more complicated figure. So the lepton is coming with a momentum from the left, as is shown in the dark arrow. It is now hitting a nucleon with a spin Sn, which is oriented generally with an angle psi with respect to the initial direction of the lepton. The lepton gets scattered, K prime. So the incoming lepton and the scattered lepton make a scattering plane. And the angle between the scattering plane and the direction of the target spin is called phi. So the total cross-section difference is then now can be calculated if you just do the simple geometric projections as cosine phi delta sigma parallel. Well, parallel means that the orientation of the lepton and the proton spin is along and against, whereas plus sine phi, cosine phi, and delta phi plus are perpendicular when you take the projection on the x-axis, on the y-axis. With the kinematics that is shown, you can then show that the cross sections for spin can be characterized by the G1 and G2 structure functions, which are shown here. The G1 is shared and G2 is here. Similarly, G1 and G2 are here. And you see that the factor gamma, which is shown here, multiplies most of these things in such a way that the G2 structure function's effect is minimized. Already, G2 is a small value, and when you multiply it by gamma square, or in this case, some function of gamma square or gamma, normally that effect becomes small. And that's the assumption I'm going to make today, although there is beautiful physics in G2 as well. We will not have time to do that. I'll refer you to some papers later in the lectures tomorrow. And now we go to measuring things. So this cross-section asymmetries that I mentioned to you before are when you have protons and the electrons spin parallel or anti-parallel, or parallel and perpendicular. So instead of measuring cross-sections, and the reason for which I will come back to in the experimental way in a few minutes, we measure asymmetries instead. We look at the protons this way versus that way, and that way versus that way. We always look at that difference, because measuring this only today and measuring that only tomorrow is going to create lots of problems. And I'll come back to those problems later. And then you can go down and create these aparallel and aperpendicular asymmetries. Then they get involved with A1, which is G1 by F1, and gamma star times gamma squared times G2, where gamma is a small number, gamma squared is a very small number, G2 is a small number, we can ignore it safely for most practical purposes. And A2, if you want to not ignore it, then you can make a very precise measurement of the deep inelastic scattering and see how different it is from G1 over F1, which you measure in this case, and estimate what G2 is going to be. So that's the method we use. These are kinematic factors. The one factor I want to emphasize is the capital D, the depolarization factor. Remember, we started with electron that emits the virtual photon, and that virtual photon then hits the quark in this picture. So there is a transfer of polarization from the electron to the virtual photon, and that is characterized by these depolarization factor. Never can there be a full polarization transfer. You always have to account for a small loss of polarization, which make it dilution in the scattering experiment. So here are the same equations rewritten some different way. I'll go quickly through that. And then you want to connect that to the spin structure function G1 with the quark's orientation. So getting to G1, which is A1 in the previous plot here, A1 shown there, G1 over F1 is aparallel in this plot here. So that's what we want to measure. And that needs to be connected to the quark distribution function, and that is shown here. So delta Qi is Qi plus minus Q bar I Qi minus plus Q bar I plus minus Q bar I minus. So I won't distinguish beyond this point, because the photon distinguish between quark and anti-quark. I will also not distinguish between quark and anti-quark. It will only see its charge and interact. So when I say delta Q, it always means the quark's orientation with respect to the proton and anti-quark's orientation to respect to the proton all together. So that's what it means here, okay? So each quark interacts with each other through gluons, which gives rise to a Q squared dependence on the structure function, as you know. And at any Q squared, the spin structure function then can be related to polarized quarks and distributions through coefficient functions CQ and CJ. I will include that in glossary. I will not go through in the detail as to what the functional forms of those are. Those are complicated figures, and you can calculate them at next to leading order or however much you can. So now let's go with that introduction as to how the measurements will happen. So remember, we are in the 1960s again. We had just discovered the quark structure. And then the obvious question was, can we then explain the spin of the quarks as well? And this is what the simple picture was at that time. That on the right-hand side, you see that the proton spin is composed are constituted by the orientation of the two quarks, any two quarks, which are orienting in the same direction, and one of the quarks will go in the other direction. So could we understand it from the similar program? I think this is something people thought we could see. So we knew how to get to the F2 and F1 structure function. So here is at the bottom here is the F1 structure function, which is the average of the quark and anti-quark, which is shown here. And G1 is the difference between them, alignment and anti-alignment of the quark flavors. And you sum over all the flavors, and then you get these G1 structure functions. So that's what we are going to measure. So let's measure the experimental, go to the experimental method. And I said summing over all spins means that in the proton you have predominantly U and D, and maybe a little bit of range. And at higher energy, again, you can start creating smaller and smaller amounts of the heavier quarks. But for most of the purposes, practical purposes, people assume that there will be large amount of U and D and a very little amount of strange. So let's look at that as in that perspective. In fact, in the earlier discussions that I will mention, the delta S, the strange quark contribution, was considered to be very, very small. So basically, the quark spin came from delta U and delta Q. And that was supposed to be equal to or related to the spin half of the proton, which is shown in the last equation down there. So we are looking for that. And here is the model that we are testing, that the proton is a UUD, neutron is UDD, and the orientation determines its spin. So let's look at the experiment. So on the left is the figure in which in this model, I have the proton with 3 quarks, dominant quarks. There are lots of glue there. I'm not showing you that. And there is a glue is always splitting into quark-antiquark pairs, but always symmetrically, so they won't matter effectively. But these 2 quarks, U and this U and this U of different color, are oriented in this model in the left direction. And the proton spin is given by this angle here. One photon comes from the electron scatter, and it can then exchange energy with any one of these quarks. When we say there is an interaction, a gamma p interaction, it is when the proton spin flips. In this case, because you're looking at a wavelength which is small enough to do deep inelastic scattering, the quark spin is flipping. And you can see that in 2 out of the 3 probability of flipping the quark spin in the first figure is 2 out of 3, because there are 2 quarks anti-aligned with the spin of the photon. As against that, in my lab, I now use the magnet to orient the proton spin differently. In this one, it was leftward. Now I've changed the magnet direction and changed it to the right side. If my theory is correct, that the quarks are contributing to the proton spin, then now I should have 2 quarks spinning this way and only 1 quark spinning that way. And in my experiment that I measure, I have a probability that only flipping of the proton spin can happen only once. So the difference between this one and that one, which is A gamma p, where this was anti-parallel minus parallel divided by the sum, is going to be 2/3 minus 1/3 divided by the sum. And I am expecting something like 1/3. There are some constants that come in front of it, which we will ignore for now and go into the experimental method. So I know from such experiment what to expect. That's what I want to emphasize. I know exactly what to expect when I have a proton, when I flip the spin and I see the difference in the cross sections. So for such experiment, I need the polarized target. I need a polarized beam. We used hydrogen, deuteron, helium. Deuteron and helium, when you combine them with the knowledge of proton, gives us information about the neutron. We need polarized beams, and typically we used electrons and muons for such DIS experiments. And then we also look at the incoming lepton, the energy of that, the energy of the scattered lepton. As you know, we need to measure that very precisely and identify to make sure that the lepton is really a lepton. And the most important thing in the spin experiment is we need to understand the false asymmetries. And what do I mean by that? So let's look at this experiment. What is shown here are those two orientations of spin. The beam is coming from the left and the top experiment. The target is sitting in the center, and the detector that detects those scattered particles is on the right hand side. And you can see the spin of the target is leftward here. And I measure, let's say, three things that come out. I measure it 150,000 times today, and I measure that. And then tomorrow I come back and I measure the orientation in the other direction, which is now the proton spin, the target spin is flipped. And I have the same detector. However, today the humidity is much higher, which means that the detector is not functioning very well. So the detector is not very efficient, or it is not as efficient as it was yesterday. So out of the 150,000 events that I saw, yesterday I saw 100,000 in my detector. Today I might see only 90,000. And I'm measuring the difference in the cross section of this orientation versus that orientation. So I see 100,000 on one day and 90,000 on the other because the detector was not doing well. That's not the physics that I'm after. Detector not being well is a problem, but it will give me an asymmetry in the calculation if I do the asymmetry calculation blindly by looking at that equation that I showed you before. If I just blindly use this equation, when the detector was not right on one day versus the other, we have a problem. So that means that we need to make these measurements in identical situations. And the identical situations don't last even for 10 minutes sometime, which means that we have to flip the target spins or the beam spins to create different orientations very, very fast. In the fixed target experiments, we would do this every 20 minutes. Every 20 minutes, we could flip the spin of the target, and every one day we would flip the spin of the beam, which was much more difficult. But if something happens within those 20 minutes and the detector starts behaving differently, we would not know. And that creates the baseline systematic uncertainty. The more often you flip the spin, the better, the smaller the asymmetries you can measure. Okay? So that's a very critical message. I will use that in the later part of my talk. All right. So the ideal situation is when the two are anti-parallel minus parallel divided by parallel is given by the number of particles of the beam, NB, number of particles of the target, the actual cross-section, the detector acceptance, and the detector efficiency. And when you flip the spin, you get the same number, but with a different one. Now, in ideal situation, if I want to simply measure that, then I should get that. But I never get that. I told you that it's very difficult to get the bare cross-section ratios. You always have to worry about these D's, which are always imperfect. And the whole experimental tool and technique that is involved, the best experiments are done is spin asymmetries. It is where the DACC and DEFF, those are the ones where the experimenters have to concentrate all the time. So how do we do that? A simple idea is the following. So we have the beam of muons, say, let's say, coming up. This is actually done at Compass experiment at CERN. I've taken it as just an example. And what they do, what we did at that time in SMC elsewhere as well, is that we take two targets and put them in opposite spins simultaneously. We run with two targets. We have one beam, and suddenly, simultaneously, we are taking data from both sides of both orientations. So this fact that we have to come back tomorrow or 10 minutes later to flip the spin is not necessary at all. So you can do this and simultaneously take data. We can reconstruct the tracks back and figure out which target it came from. So we know which orientation combination we are measuring and then separate the data accordingly. Now there is a small problem here that the angle subtended by the front target, which is shown here with the detector, is slightly different than the angle subtended by the back target. And that creates a geometric acceptance asymmetry, which we can take care of by simply flipping the spin of these two. Because if I flip the spin, I'm getting this target, which otherwise is identical, but with the spinning the other way, but sitting at a larger distance. And then this part goes in this direction. And so we can flip between the two and keep on doing that every 20 minutes and average over that. As long as the targets are filled identically and similarly, and we know how to fill them exactly identically, we are okay reducing the systematic uncertainties. So we were able, with such methods, to come to grips and perform experiments at the level of about 10 to the minus 3 or so in systematic uncertainty. So that was a major achievement that we had at CERN. So we have to now measure these asymmetries. We know the polarization of the beam, the target, the filling factor, how densely the target is filled. That tells you something about the number of protons in that area, and then the parallel asymmetry. But there is one more thing that remains, and that's a critical thing. And that is, because of the kinematics, we will never get, finally we want to get to the spin structure function and its first movement, which is shown right here. We want to go over from x equal to 0 to x equal to 1 at a fixed q square. And that is difficult to get because of the kinematics. We never get to x equal to 0. We have to do something about it, which means that we have to do some extrapolation. And the extrapolations are always very tricky. We don't know what to follow. In the late 90s and early 2000s, there were not enough information about the proton structure function, how to extrapolate them all the way to 0, because it became a very large thing. And I'll tell you how big, impactful this idea became. So here is my spin. I've measured this G1 as a difference in the quark structures. And if you look at that, explain that, and then that E square is 2 by 3 is the U quark charge. That is, square of that is 4 by 9. The D quark charge is 1 by 9, and the S quark charge is 1 by 3. So that's why you get this. And you arrange this, and you can write it as delta U minus delta D plus this factor, which is U delta U plus delta D minus 2S, which is another constant in physics. This is A3 or GA, the weak GA or GV. And then there is the AH. And this is the A0, the sum of the spin that we are after. So we can measure that from neutron decay. This came from hypron decay, and this came from our experiment. So the left-hand side is what we measure using the extrapolation somewhat, and then the extrapolation minus extrapolated first movement minus this part that came from other experiments gives you the total value of the spin carried by the quarks. And that's what we are going to, that's the method we're going to follow. And that's what we did. And these were the early results. As you saw, as we went to low x, the curve that tells you that if everything is okay, that the spin is carried by the quarks as anticipated, with some constant, that the asymmetry was expected to be here, and the data fell systematically below that. And if you integrate it to the G1 structure function, this is what the data looked like at that time, and the expected result, if the quarks were to carry the proton spin, was given by the Ellis-Jaffrey sum rule. I will not go into details of that, but that's basically where they said that the quark structures were this part here. This part here was fully responsible. They assumed delta S was 0, and delta U plus delta D at that time was blamed to be the delta sigma, and that was the disaster that you expected after relativistic corrections, some value of the order of 0.58, and we saw experimentally 0.12 plus minus 0.17. And that was called a spin crisis, because at that time it was not known what else could be responsible. Of course, that created an effort to improve the uncertainty. As experimentalist, what's most drastic to me is the 0.17. The 0.17 had to be reduced at all cost very quickly to figure out how significant this result was. Because otherwise, this is consistent with 0, which means that the quarks carry 0 spin, meaning they are not aligned at all. They have nothing to do with the proton spin. So I mentioned to you that we need to go to some rules or get to the values of G1. We have to integrate them, and extrapolation is unavoidable. The high X extrapolation, as you can see, is a small effect here on the right-hand side. The high X is the major part comes from the low X part, because that's where the problem is. So we had to go to low X with a large focus. At that time, we had not much guidance, theoretical guidance. There were the Reggie models. You might have heard of them in other lectures or in your previous studies. There were other QCD-based models that gave us some hindrance, some guidance as to what to expect. And then there were new QCD-based models which were coming up, which talked about exponential power logarithmic functions of Q squared and X. And so those all models existed, but we had no guidance as to which one was right. So we decided that what is the big difference that comes about? And here is a classic iconic plot that we made in the 1999 in a proceeding of a workshop that I presented at that time. You have the fixed target experiment sitting here. We have a next to leading order perturbative QCD fits, and that fit told me that you can go all the way down like that. With the positive gluon distribution, the G1 spin structure function bends like that. The Reggie type of extrapolations, which were very predominant before next to leading order calculations were available, showed us something like that. And there's other model dependent ones which came with other ideas. They were going up like that. So you see, there was no guidance. There still is no guidance on this. I'll show you a plot tomorrow. The situation essentially sits exactly like this. We have no new data at low X to solve. In fact, I can tell you that in 1996, 97, 98, when this is what was going on, this was my main motivation to promote the Electron Ion Collider. Nothing else that I had mentioned at that time was important. I had no idea. I was a postdoc like you guys, and I had seen this, and the only way to do that was to do a high energy polarized EP scattering experiment. And that's when I proposed the future polarized proton collider. First at Hera, and now it's probably going to be ready, realized with the Electron Ion Collider. So now let's go back and see how big a deal is this. These two people have discovered something new, something interesting, and they said, my God, look at that. We might have discovered something very important. It could be the discovery of the century. Of course, depends upon how deep this thing goes. If it ends just 2 centimeters below that, they found a pyramid-like rock. But if it goes like 100 meters below there, then they have found something discovered, important. So let's see how important our discovery was, that delta sigma is so small. Now, at that time, people started realizing that the gluons are a very, very important and an active player in the proton spin. They have spin 1. They carried, we knew by that time in the mid-90s from Hera, from the fit that I showed you before, that they carry 50% of the proton's momentum. And so now, for the first time, we realize that they may be carrying a large fraction of the the proton spin as well. So we had to acknowledge that. But because of the interactions, and because by that time we knew for a long time, about 80 years by that time, that proton was not a point particle, which meant that we had to give the quarks the freedom to move around, quarks and gluons. So now a composite picture of the proton emerges, which is a sum of the gluon and quark orientation and their interaction. It's the collective behavior of partons that generates the properties of the proton. As I mentioned to you in the beginning, the mass of the proton comes from the collective behavior, and now we are realizing experimentally even that we are measuring parts of it, and we are seeing evidence of spin coming from the collective behavior. So we have to acknowledge that the gluons have to be measured, spin, and we have to acknowledge that the orbital angular momentum of the quarks and gluons may also be non-trivial and has to be measured. So we are learning about nucleon spin. So the lesson learned was that every time we explore with spin observable, we find something new. Remember, in the previous century, there were many, many important lessons that we learned simply by looking at spin. Here again, spin came to rescue. We discovered something unusual or very deep and fundamental to QCD about nucleon spin. This is precisely the way which was done in the following decade. We need to figure out what it is that we need to measure, how to get to the remaining spin of the proton. In the meanwhile, people had explained that the delta sigma, this is Alterelli, Ross, Karlitz, Collins, and Mueller, they said, well, the delta sigma that you're measuring is a q-square dependent factor, which is the bare minimum independent q-squared independent one times the alpha s times delta g. So if the delta g is large, then alpha s times delta g is large, and some of this will be taken over by the delta sigma. So as long as the delta g is large, you should be able to measure it somehow. And that's the message that we were given by the theorists at the time, and say, go measure the spin of the gluons now. And that's what we started measuring. The high X part is less important, but we will measure it anyway. So here is a lot of experiments were launched, primarily to reduce the uncertainty on delta sigma from 1.7 to a smaller number on 4 different continents or 2 different continents. In DAISY, Europe, Hermes experiment was launched. Experiments at SLAC and Jefferson Lab were launched, and the CERN experiment was also launched. SMC made experiments very precisely and then followed up with COMPASS. So here are the cartoons or the figures that were there. Typically, you see they are electron experiments. The Hall A is an electron experiment. You can move the spectrometers to do q-square dependent studies. Hermes is a very forward calorimeter detector here. The target sits here. The beam comes from left and a very forward acceptance. They also put particle identification to study flavor separation, similar to the one that now has evolved into the COMPASS experiment at CERN on the right bottom here. The only difference between them is that the COMPASS experiment, unlike the others, measures muon scattering. So they can go to higher energy of the muon, 200 GeV, 160 GeV, but the electron beams are typically 10 to 20 GeV. And that affects the xq square plot. And that's why the muon experiments can go to the lower value of x, because they have large center of mass energy. So here are the precise data on proton and deuteron, plotted on x and q squared, again, separated for various values of x. And on them are now plots of the best fits to next to leading order. Very similar to the F2 structure function fits that I showed you before. The difference is that these are now G1 structure functions. The left plot is for the proton and the right plot is for the deuteron. And similarly, before I told you that the slope of the F2 structure function gave you the gluon distribution. Here, the slope of the spin structure function G1 gives you the gluon spin distribution, delta G, as a function of xq squared. But there is a problem. And the problem is the following. The xq squared of these fixed target experiments take you only to the value of x, which is 0.0036 on the left top here. You see that? In the proton, just below the proton, you see that it is 0.036. In this case, it is 0.0045 in deuterons. You see that here? Right there. And the q squared range is also fairly limited. It's from 10 about 100 GeV. If you remember, for Hera, we went to 10 to the minus 5. And the slope of the distributions were in the very, very low x region, which is where the gluon resides. And here you see that all the plots seem to be flat. As a function of q squared, all these curves are flat. Q squared is on the x-axis here. So if you try to get the slope, you get a very nice fit, but you don't get the slope, which means that there is no glue. If there is no glue, you can't measure it very precisely. And that is then reflected in the kinematic lesion. So this is the kinematic edge on the xq squared I showed you in green lines. And if you compare that with the Hera, that same kinematic line sits on the left bottom there. And the point of my argument to go to lower X, meaning to go to higher center of mass energy like Hera, to polarize the collider, is the fact that the gluon is sitting here in the low X region where the slopes are significant. If the slopes are significant, we can make measurements precisely of the gluon distribution. If you measure things only in this bottom corner region, you will not have a very good handle on the gluon distribution. And that is one of the main reasons we proposed the polarized Hera first and the polarized collider. And this was the result from 1998 that was published. And you can see the gluon distribution inherently has large uncertainty. This is the experimental systematic, and then this is the theoretical systematic in the next to leading order calculation that we did at that time. And not surprisingly, the gluon's distribution and its first movement as the gluon's contribution comes out to be 1 plus minus 1.5. Remember, we are looking for the total proton spin to be 0.5, and I'm getting part of that, of delta G, to be 1 plus minus 1.5. And that's precisely because we don't have the leverage to do the precision measurement. By the way, we did one thing right, and we measured the delta sigma very precisely. That came out to be 0.23 plus minus 0.04. Remember, this was 0.17 before. So we did very well on that front, as expected, because we are measuring things in the region where quarks reside. We are really at the edge of places where gluons live. So that's why the gluons are very unsatisfactory. We have to do something different. The consequence was this. Eventually, we found that over time, this value of delta sigma has evolved with better estimates of the uncertainty, etc., to be about 0.3 plus 0.03, and the delta G is about still at that point 1.15. And as I said, the reason is this, that this red line here is this same red line there, and we want to go in the region where actually the gluons live. So we need to go to higher energy, and we need the polarized electron-proton collider. And that was the beginning of the Rick Spin program. So I'm exactly at about 55 minutes, which is where I want to be. The chair told me someone wants a small break. I can stop for 5 minutes. If you have questions, I'm happy to take them. I don't need to stop. I have my water and my coffee sitting here. So please let me know. Okay, 5 minutes. Okay. Yes. Yes, hi, how are you? Very good. I'm sorry I'm not able to talk to you in person. I said, I'm sorry I'm not there in person. Yeah, I had a back problem last week, so. Yeah, I couldn't. I tried to sit. I couldn't sit for 10 minutes last week, so I couldn't have flown. I mean, otherwise, if I stand and walk, it's okay. But if I sit, it's a problem. But now it's okay. Now it's coming back fair. I'm strong again. How are you doing? Uh, uh-huh. For the gluon GPD, for the gluon JPSI production, for JPSI production, yes. So I can send you. So send me an email. I can send you some comments on that. I know some people are working on that. There are in the white paper we had some early physics where we looked at the gluon distributions as a Fourier transform of the T distributions. You know about that, right? I have to look at that. Yeah, I don't remember offhand, but I understand what you're saying. Send me an email with specifically describing this, and I'll respond to you. I'll look at that. I know some people, um maybe Hata-san, Yoshitaka Hata. Okay, so I know he has started working with a student recently, but I don't know whether it is exactly this problem. But I know that he was interested in Upsilon production and JPSI production at the EIC. So I will talk to him if there is someone who has started working on that. Janway might also know. I'll call him up. But send me an email explicitly with this. So that's a reminder to me. So I will then look at that. Okay. Okay. Very good. Very good. Okay. You're welcome. You're welcome. How is the weather there? You sorry? Oh, okay. Go. Go. Yeah. Go. Go. Okay. Yes. Yes. High X. Yes. Yeah, I believe that we will maintain ability to look at geometries in which you get very high X. So the detector will be able to look at those geometries, if that's what you're asking. So my expectation is that we will get to maybe about 0.8, 0.9, maybe 0.85. I think we can get there in X. Well, the reasonable statistics are basically given by nature, cross-section. So we will try to do that as best as we can. I had a student, a postdoc on HERA in 2006. She did an analysis. She's a Columbia graduate student with Alan Caldwell. And we did up to about 0.9 at HERA. I don't know whether you know that. Yeah, so there was an effort to do that, to really see how much we can do. So if even at HERA we had events which we were sensitive to at 0.9 with very low efficiency because we just didn't have the right orientation. So I believe that the EIC will do much better. I haven't revisited that recently, but clearly it will be possible. I would like to get that. It's on the back burner so far. So I think that what will happen is we'll have to combine data from JLab 12 and EIC to get the Q-squared arm. Because I'm not sure that we'll get individually enough Q-squared arm. Okay. I will send you a link. Again, mention this in your email. I will send you a link to this PhD thesis, or if not, I will scan that thesis. I have a thesis of that student. And I think I should be able to find it. It's somewhere in that box there behind me. So I will find it, and I will at least show you what was done at HERA. And then maybe if you want to, we can talk about this a little bit more detail and write a small note to make the case, and maybe let's calculate a few things and see what it would take. So if we write it doesn't have to be a long paper. It just says what's the motivation and how we think it might be possible or not possible, whatever it is, right? So maybe 2-3 pages, just a note, and then we circulate it amongst people who are making the plans for design. Yeah. Okay, very good. Okay. Okay, excellent. So let's start with where we left. What we had now summarized is that we understood by this time, late 1990s, that the quark spin was not going to explain the proton spin. There was initially no reason to believe gluons might play a role, but apparently they did. They were blamed on the entire spin of the proton at that point was blamed on the gluons. But at the same time, I'm going to show you how biases in physics can lead us to wrong decisions for a long time until a corrective process has to happen. So these are lessons that we have learned, I have learned in my lifetime. And I think you should keep that in mind. So the transverse spin puzzle. From 1933, we knew for sure that the proton was not a point particle because of the anomalous magnetic moment. Once we learned that partons make the protons, people had theoretically at least must have wondered that there must be a transverse motion or some motion of these quarks inside. And that meant that it had to have a transverse component. But we never needed it because Feynman told us that the only thing that matters is the Bjorken X, the X-dimensional directional motion. So everything that we knew at that time could be calculated using this X, Y, Q squared, etc., etc. So we really did not need it. But as the technical designs of the experiment and tools became more and more precise, people were measuring things that we could not explain. And I will come to that a little later. And that's the transverse spin puzzle that I'll talk about in the second half of this remaining lecture. So we are now saying that the gluons are responsible. And we also know at that time in the late 90s that protons are predominantly gluons. I told you the Schrödinger plot where the gluon distribution is the dominant distribution below x of 0.1, which means that most of the partons inside the protons are gluons. So a simple question is, why not use polarized quarks and gluons inside the protons themselves as the probe? Let's polarize the protons and collide them at high energy. Polarization of the proton is non-trivial. But fortunately, we were able to do it. We were close to doing it at the turn of the century, from 1900s to 2000. And that was done at the relativistic heavy ion collider. So here is a schematic of the collider. What you see in the collider is 3.8 kilometers around. So you can have a very good exercise if you run on the road inside in this collider. The polarized H- sources is sitting here in the left bottom. They are accelerated by the LINAC, pass through a very high intensity, high electric grid, where they strip the H- off of 2 electrons. And that means that now we have a proton that goes into the booster, gets accelerated to 2 giga electron volts, 2 GeV, gets transferred to the AGS, gets transferred there to about 24 GeV, and then it comes out here and goes alternately in the blue and the yellow ring of Rick, which then is able to accelerate the protons up to 250 GeV. This was unprecedented, and it was made possible by very special magnets called the Siberian snake magnets, which are shown here and which are shown there. There were 2 sets in each ring. And now what I'm telling you is that the orientation of the protons, which is normally perpendicular to the direction, the plane of the rotation, we have to manipulate that because we are looking for how many of the gluons are aligned with the same direction of the proton. So the collisions happen again longitudinal parallel versus longitudinal antiparallel. So this is the same thing that we did before in the deep inelastic scattering. However, now instead of using a muon or an electron, I'm using a proton, and I'm assuming that inside the proton are quarks and gluons, which are then colliding with the quarks and gluons of the other proton. And the asymmetry that comes from the quarks is understood because that will be related to the quark spin. And the asymmetry that might remain, that we might measure, that might be not explained by the quartz spin is really what comes from the gluon spin. So to orient these, we have to have these special magnets called the spin rotators around the experimental area. There are two experimental areas, the Phoenix experiment and then the star experiment. And before and after that, there are these spin rotator magnets that rotate the transversely polarized proton into longitudinal, this way or that way, and then make them straight again as they come out on the other side. This has to be done twice for the experiments at the two sites. The Siberian snake magnets are very, very special magnets. They help maintain the polarization of the proton. How do they do that? So what happens in acceleration, and these are the diagrams that are shown here, you can see that how the welding is, how the winding of this thing is about 2.6 meters. That's really what it is. And that's how it looks like inside here, inside the magnet. These were built by Riken in Japan and Department of Energy, one of them each. And as you pass the proton, the thing about this magnet is that if you look at the bottom center, is the orientation shown with transversely polarized proton entering from the left side. And if you look at the right side, the proton is on the same straight line back again, but now it's oriented 180 degrees, oriented differently. So that's what a full snake means. In 2.6 meters, this is what it has to do. That means that the orientation, the strength of the magnets has to be extremely large. But we are talking about 100 to 250 GeV proton rotating like that in 2.5 meters. That's tremendous. And the shape at which it goes inside the magnet, it doesn't go like a magnet straight line. It goes like a snake winding through this. And that's why the name snake. And the idea for building such a snake originated by two scientists who were working in Siberia, in Russian collaborators. And that's why this magnet is called the Siberian snake magnet. They were built first for high energy at Riken and at Brookhaven. That's the only place in the world in which such magnets have ever been measured or built, other than smaller strength magnets which were tested at Indiana University before that. So the world's only collider is like this. These are the experiments, the Phoenix experiment. The top view tells you the beam's view. The beam is going into or out of this plane. And then you have the collisions in the center. The bottom view is the side view. So the beam is coming from the left and the right. The collisions happen in the center. And the various beam counters, the microvertex detector, the muon trigger are shown here on the forward and the backward region in the bottom. And on the side, we have the drift chambers, the particle identification, the lead calorimeter sitting at the back, etc., etc. The star detector is shown here. That looks a lot more like a collider detector, a full 2-pi acceptance. And again, the collisions happen in the center, the beams come from left and right, and various detector components are mentioned. For spin experiments, I told you it's very, very important to measure these cross-section plus minus. And now we have the polarization of the proton as goes as the dilution because we don't have 100% polarized beams. So instead of the F and D, we have 1 over P1, P2 of the two polarizations. And then we have this correction factor R, which is the luminosity up and luminosity down, or parallel versus anti-parallel. Remember, those differences at the physics level is what we are looking for. However, if the detector is doing something funny between the change of plus and minus, then I told you that I will get a false asymmetry. The detector changes can create the false asymmetry, but so can the beam. So suppose that the bunches of the beam are filled with positive direction of the spin differently than the negative direction, orientation of the spin, then this kind of asymmetry will come because of the fact that the colliding bunches this way versus that way are looking at different numbers. We are not interested in that. We are looking at the physics asymmetry that comes from inside the proton, not the mistakes I made in filling up the bunches. So that needs to be monitored extremely carefully. That's one accelerator physics problem that we need to solve. But the detector-related problem is solved very easily in colliders. We fill the beam, one coming this way and one coming that way, with different spin orientations. These are different bunches, plus, plus, minus, minus, plus, plus, minus, minus, and each bunch is separated by 100 nanoseconds. Nanoseconds, 100, which means that we are flipping. That's easy to do because we are just filling the bunch that way. The other bunch we fill like plus minus, plus minus, plus minus, plus minus, plus minus. And the collisions happen this way. You have the plus on the left hand side hits the plus on the right hand side first. So you have the L plus plus. Then the next one is a plus on the left and minus on the right. Then I get plus minus. Then the next one I have a minus plus. Then I have a minus minus. The minus minus and the plus plus physics should be the same. Minus plus and plus minus, the physics should be the same. So then you can do all kinds of combinations. And since these combination of different orientations happen in 100 nanoseconds, the detector for all practical purposes is the same between plus plus and plus minus. Remember, in the fixed target experiment, that changed every 20 minutes and every 1 day. That means the detector could change between those spin flips. And I told you, the more often you can change the spin in these experiments, the better control you have on the spin experiments. So the false asymmetries can be smaller and smaller. And that's exactly what happens in here. And that's why in the collider, surprisingly to many people, we were able to control the systematic uncertainty due to false asymmetries like that to a value which was 10 to the minus 5, which was very, very impressive. No fixed target experiment, at least at that time, had attempted or tried to do that. So we have exquisite control over the false asymmetries due to ultra-fast rotation of target and probe spin. So now let's go back to getting back to the double longitudinal asymmetry. We are measuring now pi pluses, pi minuses, something like that. Direct photons, for example, coming from PP scattering, and you start making these ratios of cross-section asymmetries. And what you need is the polarized spin structure functions of the target and the probe, of the beam and the probe, that's two protons, the cross-section that comes from external leading order perturbative QCD, and whatever we are measuring in the final state, we have to see this, the pi plus, pi minus fragmentation. That comes from either E plus E minus or SIDIS. And then we can start seeing what the distributions looks like. And for at least for pi pluses, we look at, for this is a fraction of the pi zeros produced from various processes. The gluon-gluon process dominates at low PT. The QQ is the green here, and QG and GQ is sort of flat here. So if you go to low PT, it's this process that dominates, the gluon-gluon, and that's what's most sensitive to the glue. So we can get the gluon spin. As you go to higher PT, you start getting complications due to QR-quark-quark and quark-gluon. We need to incorporate that. But the basic experiment is done with this kind of collisions, where the protons are anti-parallel versus when the protons are parallel. And we make measurements. On the right top is the double longitudinal asymmetry of the pi zero production made by Phoenix experiment. And you can see they're very, very small numbers, but you can see a slight trend in going positive here. More recent data from TAR for jets, PP to jet, shows clearly that you have non-zero positive asymmetries associated with the jet production. at 200 GeV in the center of my central rapidity, and here and then also in the forward rapidity. Now let's look at what theorists did with these data. They took this data and put it in the global analysis and showed us that you can extract the polarized gluon distribution. So what is shown here on the x-axis is the log of x, or x on the 10 to the minus 3, which is where our measurements end. And on the y-axis is x times delta G, the gluons distribution. So coming from this publication, which is a global fit. It is shown at q squared of 10, and these are various curves that are allowed. The blue is the best fit with the most modern data set. The curve under, the area under that curve is the total gluon distribution function. The red is 1 sigma away positive side, and the black dashed line is 1 sigma away negative side. And you can see approximately with what variation, what the range in uncertainty is. The measurements of the RIC came in between these two regions here, shown by the RIC range that is shown here. So it didn't do much to do anything on the low X side. So the last slide from my previous part of the lecture that said we have to go to low X, we did not make a lot of dent. However, we did reduce the uncertainty in this range here. So if I take the value of measured value of 0.01, which is right here, all the way to 0, or 0.001 to 0.05, which is this part here, that is plotted from that curve on the y-axis of the right-hand side plot. And then on the right-hand side is 0.05 from this range here all the way to 1. The integral is going there. That is plotted on the x side. So you can see that before the RIC data, we had a large uncertainty in both directions. The green blob is shown here, with a small value of gluon distribution shown by the blue. After the experiment, we have reduced the uncertainty in the region where we have made measurements by in the blue region there, X range, and that is shown by the reduction in uncertainty in the X dimension. So the green becomes horizontal blue. However, because we did not take any new data in the low X region, the unknown, the 0.01 to 0.05, which is the up to this point right here, there it makes no difference. So there the uncertainty is still very large. So what is shown in this plot number here is only in that X direction. The large uncertainty in this direction is not shown. As you can see, it is of the order of about 0.5 itself. Large number. We can't really do that. We really need to go directly and measure that part. And that will be done by the Electron Ion Collider in the future. Now let me step back and show you some theoretical biases that influenced our measurements and our judgment. So in 1978, there were some measurements which were performed just as curiosity at various laboratories by Alan Krish of Michigan, University of Michigan, where he collided transversely polarized protons. You see the left figure there, the green arrow shows now the proton is transversely polarized. Remember, this was before the advent of the Siberian snake magnets, so there was no way to turn them over to do longitudinal spin. So this was all he could do. And he hit that with the unpolarized targets, and he observed that there is a pion produced in the PP scattering, and he measured how many of them are produced on the left versus how many are produced on the right. And he made this kind of an asymmetry, AN, normal, he called it a normal, that is the normal direction, to the left, number of pions on the left minus number of pions on the right, divided by the sum. And he was measuring large asymmetries. He was measuring something like 40%. So these theorists, Kane, Pumpling, and Repko, they estimated, using their knowledge of QCD at the time, that these asymmetries, if they came from QCD orientation, or the knowledge of QCD, they should be of the order of the mass of the Q, the charge, the quark, the leading quark inside the pion, that is U quark, divided by the transverse momentum that could be of the order of a GeV. Alpha S at that energy is large, so that alpha S was measured. And so they estimated that that should be very, very small, 0.001, that is 0.1%. So the argument amongst theorists was that that asymmetry cannot be so large, cannot be explained. And I'll show you some results later. But basically, people said that there must be something wrong with the experiment. And so they ignored it for a very, very long time. What were those experiments? You look at these measurements in 1976, 2002, in 1991, in 2008. And I'm going to compile them in a very similar way. Pi pluses systematically go up at 4.5 GeV, a center of mass, at ZGS at Argonne National Lab. The pi minus tend to go negative. And you see the value of the asymmetry is of the order of, let's say, 5% going all the way to 40%. The experiment was repeated in 2002, published in 2002, actually performed a little earlier, 4 years earlier. It was at 6.6 GeV, and again, a very similar plot, very clear indication that the pi pluses go positively, pi minuses go negatively. At 19 GeV, at Fermilab, they made the measurement, again, positive and negative. And finally, at 62 GeV, they saw this again. When the expectation was 0.001, we were seeing something of the order of 400 times larger asymmetries than were expected from the theory, a simple theory. So this was initially blamed when the center of mass energy of the experiment was small, 4 GeV, on soft QCD effects that were of no great consequence to the perturbative QCD that everyone was after. But last but not the least, at RIC we measured it even at 62 GeV I mentioned to you, which already made it very dubious that calling it a soft QCD effect. But we measured it at 200 GeV, 200 GeV center of mass, and those asymmetries very clearly existed even then. That was the last straw on that argument that these are either not mistakes and these are not soft QCD effects. But what are they? Because proton-proton system is a lot more complicated system, there are many things that can happen. And those many things are very difficult to distinguish among themselves. And that became the most difficult thing to do. And that remains, to some extent, the enigma. In the meanwhile, people have done transverse spin experiments with electron-proton scattering. We see those same asymmetries, left-right asymmetries, when you have a polarized proton which is spinning transversely upwards. When the electron hits it, kicks a pion out, the pion predominantly, pi pluses, go to the left as they were seen in the past experiments in PP, and pi minuses go to the other side. We have repeated such experiments with kaons, and kaons show a completely opposite behavior. The k minuses go to the left, and k pluses go to the right. And k minuses are S bar U, and S D bar, U D bar, US bar, and US. And that's why you can play with this combination and confuse yourself completely. But the systematic effect that you see is identical at all energies. That meant to us now in the modern formalism of understanding of QCD that really the quarks must be responsible for that. There must be a transverse momentum distribution. The field of transverse momentum distribution, TMDs, evolved out of such surprising observations. Again, experimentally driven field, spin playing a critical role in letting us know that something unusual is going on in the structure of the proton. So here is one way to get a left-right asymmetry. So here is the example. This is the proton. The spin is coming out and it hits the target, which is a proton with a transversely polarized target. And then you see a left-right asymmetry in the quarks that come out, that comes from the helicity times the KT of the polarized quark. Helicity of the incoming quark and the transverse helicity, momentum of the quark in the target. And you can get partons that come out this way on the left or right side, and that is called what was predicted or envisioned by John Collins, and it's called the Collins effect. It comes from the fragmentation of quark into the pion, fragmentation region. The Collins effect or Collins-Heppelmann effect. The other option is that the initial state itself has a distribution of momentum. If you have a record or a disc, musical disc, I don't know, you guys have probably not seen a gramophone, but maybe in historical movies you've seen a gramophone or a CD in the modern part, and it rotates on the disc on the player. But if you take a small coin and put it on one edge, and it rotates along with the record, and you know it's a circular motion of the coin. But if you watch it from the horizontal direction, it looks like the coin is going back and forth, left, right. That's simple harmonic motion. So the rotation looked at from one angle is the simple harmonic motion. What we're claiming now, that the quark rotational motion inside the proton might be affecting the pion production depending upon when the hard probe, gamma star, hits the quark. Most often the quark is hit on the front side. So here is the hard probe coming from the right and hits a quark, and that quark will then predominantly go to the right of this, and you will see that red shifted. If you hit the quark coming at you, it will be blue shifted, and you can start seeing these effects either in left-right asymmetries or something called deeply virtual Compton scattering that we will come to tomorrow, where that excited quark then emits a real photon, and that distribution can be calculated and now even measured. So the idea of such a thing came from Burckhardt. I think this is a slide that I took from Burckhardt, where you start thinking about the spatial distribution and the spatial motion in a complete way. Sivers envisioned this, and so this is called the Sivers function. This has now been incorporated formally into the theory of what we know of the proton structure. This is the initial state interaction, initial state of the transverse motion of the quark that gets affected, is affecting what you see in the final observation. And that's why it is related to the orbital motion or possible orbital motion of quarks inside the proton. So to do this, again, to summarize all this, so the protons and neutrons are not as easy as people thought before to understand. Simple alignments of quarks and gluons do not make a proton. We now know that there could be orientation and possible orbital motion. That orbital motion and the angle and the energy of, not the angle, the energy of that dynamics that happens inside the proton, as I alluded to you before, is also the reason for the proton mass being so high compared to the bare quark, constituent quark mass. To fully understand the proton structure, including its spin, we need to go beyond the xq squared. For the reason that I told you before, we have to go to a region where gluon dominates the QCD landscape. Only then can we measure its spin. If we don't go in the low x region and the high q squared region, we will never reduce the uncertainty in the gluon's orientation contribution. So we need a much broader xq squared range, which is not possible in fixed target experiments. We need to go to a collider. And then last but not the least, we need to look at, and that's the low x behavior, but not the last the least, we really have to understand what the dynamics is. I alluded to the fact that we will have to measure the orbital motion in C2, which means that you will have to look inside the proton without breaking the proton. Till now, we were doing deep inelastic scattering. We destroyed the proton every time. We did not care about the proton. But if you really want to measure the angular motion, we have to not destroy the proton. And that means as an experimentalist, I have to make sure that in the experiment, I measure the final state of the proton, which means I have to measure it. And I have to make sure that I was actually probing the quark inside. And that's that new process that I mentioned to you called the deep inelastic scattering with virtual Compton scattering, deeply virtual Compton scattering. And I will come back to that a little bit more detail tomorrow. Let's revisit very briefly what do we know of the nuclei. Very similar to the polarized protons, the EMC experiment, particularly at CERN with muon beams, which discovered the spin crisis, also discovered a nuclear structure crisis. Here is a schematic representation of what we know today. What is shown on the x-axis is the X-Bjorkane. On the y-axis is the ratio of the F2 structure function, not the spin, the unpolarized structure function of calcium divided by the unpolarized structure function of the deuteron. For all practical purposes, deuteron can be taken out and you look at the proton as well. This is the same plot you will get, but deuteron is stable and we could measure it at that time. And that's basically it's the ratio. The fact that this is not this equal to 1, this ratio over a wide range in X is not equal to 1 was a big surprise at that time. Especially that was measured first with the EMC, which is open points right here, open circles which are shown there. This is how it was seen, and that was shocking. People did not expect that. People thought that it would be almost the same. What it tells you is that the proton moment or the parton momentum distribution inside the nucleus starts changing as a function of X over that range in X. And what is increasing as you go to lower and lower values of X is the gluon component. And that means that the gluons are also playing a rather significant role in the very, very low X region. The only problem with this plot, and I'm sorry I did not write it down on this one, that the measurements that were made with the EMC, the low X data, also were made at very low Q square, which were almost lower than the Q square of 1, or very close to it. which meant that people were unhappy about those measurements, saying that these were not in the perturbative regime. So again, many soft QCD effects could come into picture, which were more difficult to explain. So it is required in the future to measure these structure functions in the perturbative regime, where you can manipulate calculations and explain the gluons at q squared sub 10 GeV, say, or 5 GeV squared. And you cannot do that in fixed target because you don't have enough kinematic reach. You only can do that with an EA nuclear collider. And that has never been measured. The second question with this, so this is the region where we want to go, with high q squared and very low x. The second thing that is of curiosity, and I mentioned it to you before in my lecture, and I saw in some of the slides that Dan Brodsky has shown, there are very, very interesting questions about how color behaves inside the nuclei. With light quarks versus heavy quarks, when a parton is pushed by a collision like this shown on the left-hand side in the cartoon, the color traveling through the nucleus and then coming out at some point after hadronization or fragmentation into a hadron, it either happens just at the boundary outside, or it could be happening inside. This would be a color neutral object traveling through a colored system. Whether it happens this way or that way, we don't know yet. The reasons are many. Many of them are experimental. Remember, in fixed target experiments, you have a large number of targets sitting at one place. And if you do this experiment, what comes out here has to then make through the solid state targets that are typically existing for most of the nuclei. And that means that the attenuation of what comes out is very quick, and you will not get too many things to be observed. So although we saw that there was a depression in the F2 structure function, which did not require the knowledge of hadrons, we were only measuring the scattered electron and the scattered angle, that was enough to get those plots. It is very, very interesting in the future to overcome that. And the only way to overcome that is to go to colliders where the nuclei are not in form of solid state, but they are gaseous blobs of bunches in a collider. So there are lots of them, 10 to the 12, 15 of them in a bunch, which might be a few centimeters long and a few microns wide. So it's like a gas of iron or a gas of gold, which means that if I do this experiment and the hadrons come out, I have a good chance of studying that systematically. And then I can study this very, very systematically by changing the energy of the photon. I can change the size of the nucleus. I can go from proton to neutron to lithium to carbon to silicon to iron to gold to lead to uranium. And at RIC we have learned to run all these atoms, nuclei. So we can change the size of the nucleus and change the color, the length through which you can control things. There are things about the color transparency that I think Stan might have mentioned in his talk. Those things can be very systematically measured. So all the predictions that are based on various models and very limited knowledge of deep inelastic scattering on nuclei from the past decades, and has not gone forward because of lack of new technique, can be addressed extremely carefully, extremely systematically, and extremely elegantly in the future collider. And I told you in the beginning that color neutralization or fragmentation is really a process of inverse of confinement. So in my mind, I view this as extremely critical clues to understand confinement. I don't know. We have to get those data. We have to see what it means, discuss and sit down with bright people like the speakers, the other speakers of this conference, of this meeting, like Stan et al., and put them all together, that information, the experimental as well as the theory information, and try to understand what the confinement is all about. How does the parton know when to stop going away from the center of the proton? If it is moving, remember there's a transverse motion of those partons. It needs to know when to turn around. And that means that turning around also gives rise to this angular momentum. The same thing I'm coming back to is that coherent motion, the emergent dynamics of partons, is responsible for the TMDs, the GPDs, the distributions, and that must be intimately connected to fragmentation, neutralization, and hence confinement. So all of this has to be measured very systematically. On the right-hand side bottom, I show you a plot of our knowledge of fragmentation function of heavy versus light quark. And you can see that as a function of z, which is the fragments, the pions or the final hadron's momentum, as a ratio of the photon's momentum that created that hadron in such a process as the nucleus. You can see that the light quark's fragmentation function is very different than the heavy quark's fragmentation function. Those differences then result in experimental designs that we will consider tomorrow to be considered differently and to measure them systematically. So that's something that we absolutely need to do, and keep these things in mind for tomorrow's discussion. You need a nuclear collider, an EA collider, which affords not only precision because of the electron scattering, but control also because of the electron scattering. And the nucleus importantly gives us the size, the femtometer detector that we are looking for in this kind of physics. And that's the reason for the electron ion collider, from the nuclear side at least, to start with, which we will consider tomorrow. So I think I will stop at this point, and tomorrow I will start with the more detailed